I'm Tijana Todorovic, and as you heard, I'm a PhD student at KTH at the Department of Fiber and Polymer Technology and Division of Coating Technology. And the project I'm working on is related to adhesives for wood based on side streams from the pulp industry. And my supervisors are Eva Malmström and Linda Fogelström. So why we want to use these hemicelluloses for adhesives? Wood adhesive market is increasing every year, and these adhesives are fossil-based, which means that they are not from sustainable resources. So if we can use wood hemicelluloses that originate from the forest, then we can improve sustainability in this area. And also, if we are using side streams, we can add value to these side streams if they are used as wood adhesives. So in a project, we are formulating these wood hemicelluloses with additives, so we can higher their molecular weight and improve bond strength. And also, depending on additives that we are adding, we can improve water resistance also. To understand how molecular properties affect these bond strength of these adhesives, we are using well-defined hemicellulose as a model, and we are modifying its molecular weight with hydrolysis, and then analyze how this molecular weight changes will affect bond strength of the adhesives that are made only from hemicellulose and wood. So the aims of the project are to develop this wood hemicellulose-based adhesives, to investigate how these molecular properties affect the bonding properties. And today's presentation will be focused on this part of the project, and then also to correlate molecular weight investigation, the results we have, with pulp-process hemicelluloses. So we are using, as a hemicellulose model, Locust Bingham. It is a hemicellulose that is extracted from carob tree seeds that you can see on the picture. And it is a galactomannan with mannan backbone and galactose units as side groups. And these galactose units are randomly distributed along the mannan chain. And the ratio of galactose and mannose in Locust Bingham is 1:4. And why we decided to use this Locust Bingham as a model is because in previous studies in our group, Locust Bingham showed good bonding properties, and you can see on a graph that it has high strength, both dry and water resistance. This is re-dry strength of the adhesive, and this is compared to well-known polyvinyl acetate adhesive that is used in wood industry. Also, Locust Bingham has high molecular weight, over 1.3 million Dalton, and that allows us to have high molecular weight that then we can hydrolyze and make different molecular weights that we will investigate later. So we're using hydrochloric acid, and we are doing acid hydrolysis for this. We are using temperatures 60 degrees and different times from 0 to 6 hours. And you can see that at the beginning, this hydrolysis is faster, but then with longer time, the rate is slower. And we have different molecular weights with, of course, different times. And these reactions results are reproducible, so we can do it more times and have the similar molecular weight. To see if carbohydrate composition is changed, if it's still 1:4 as from the beginning from a pure Locust Bingham, or if the hydrolysis changed this ratio, we did carbohydrate analysis, and you can see it showed that the composition was nearly unaffected after hydrolysis. That means, and high molecular weight affected. So that means that when we take these hydrolyzed samples and use them as a wood adhesive, we are analyzing effect of molecular weight and not composition. And when we want to prepare Locust Bingham as an adhesive, we dissolve it in water. So Locust Bingham is not completely soluble in water in elevated temperatures. Most of Locust Bingham is, but one part, smaller part, is not, so it is only dispersed in water. We apply adhesive between 2 wood veneers, press them on elevated temperature and pressure, and then we determine tensile shear strength of these samples with wood veneers. And when we were preparing adhesives, we used the same dry content for the beginning, and then later we tried to higher the dry content and have higher viscosity, and you will see later why we decided to do that. So yeah, high viscosity, that will be the same, similar for all the samples. And we also did the different applications with 1 layer and multi-layer. So dry content from the beginning was 5–8%. It is low for wood adhesives, but that is the highest that we can get with the Locust Bingham, with non-hydrolyzed Locust Bingham. apply on one layer, and also that means that applied amount of dry adhesive. So it is adhesive that is on veneers after water evaporates during pressing. It's 18 grams per square meter. And you can see on the graph that with the decrease in molecular weight, the bond strength is also decreasing. And you can also see that there is two phases. The trend is different with the different parts. So with high molecular weight, when it's going from 1500 to 500 kilodaltons, the strength of the adhesive is changing slowly. But after that, when it's a lower molecular weight, in that region, effect of molecular weight is much higher. Because, as I said, 5% is low for wood adhesives. We also did the multi-layer application, which means that we apply one layer of adhesive, leave it water to evaporate, apply another layer, and leave it to evaporate until we got to 4 layers, and that would correspond to wood adhesive that has 20 weight percent dry content. And you can see that with more adhesive on a bond line, the strength is higher. But also you can see again that there is different effect of molecular weight depending if it's high molecular weight or lower molecular weight. And on these small pictures, you can see how these adhesives look like right after application on wood veneers. And you can see that viscosity is different. So with the lower molecular weight adhesives, the viscosity is lower. And the problem with this application is that it's very easy to squeeze out the adhesive from the bond line. So when we put them between veneers and press them on elevated pressure, these adhesives that have lower molecular weight, they are squeezed out from the bond line. And that means that after pressing, we have less adhesive that we initially wanted to have and to analyze. So that is why we did the higher dry content, so we can target the similar viscosity of all adhesives. And with one layer again, so on this graph, you can see how that affects. So all these adhesives, it's only for 500 and 300 kilodaltons molecular weight, but you can see that all these adhesives have the same, samples have the same adhesive on the bond line. But when it's higher viscosity, higher dry content and higher viscosity, then the bond strength is improved. And that is because with higher viscosity, it's not easy we cannot squeeze out the adhesive from the bond line, which means that in the bond line, we have the initial amount of the adhesive that we actually wanted from the beginning. So to conclude, we did acid hydrolysis and the molecular weight was decreased, but the composition was nearly unaffected. When molecular weight decreases, the bond strength decreases with more effect in lower molecular weight regions. And also when we have optimal molecular weight of hemicelluloses, that allows us to have higher dry content and then still have facile application, but in that case improve the strength. And also we saw that low molecular weight hemicelluloses in this study did not give sufficient bond strength. This also we also saw this when we used Pulp-process hemicelluloses. So the other part of the project, as I mentioned from the beginning, is to formulate these wood hemicelluloses with different additives. And here you can see that we formulated together with higher molecular weight biopolymers and to improve bond strength. And so you can see that with it's only hemicellulose, it has very low bond strength. But when we add higher molecular weight polymer, the strength is higher. It's improved. But the problem, the same as we saw in a hemicellulose model study, is that with increasing this high molecular weight biopolymer, we are also increasing viscosity. And that is the problem because for some applications, it is important to have different viscosities and to be able to apply or even spray adhesives on wood. So for example, with 95% or 75% of hemicelluloses, it is much easier to apply these adhesives on wood. So as for hemicellulose model, also with this study, we saw the same trend. We need an optimal molecular weight that will give us high strength, good enough strength, but also to have very easy application. And I would like to finish with thanking Treesearch and other organizations and also industry partners that made this project possible. And also to thank you for your attention.